Hello and welcome to this video. In this video, we will look at insertion and search of binary B plus trees. So in previous video, we have covered the theory of B plus tree. In this video, we will look at the implementation. So there are two implementations we are going to look at. Not really look at. One I will exactly explain. The other one is for you to study. So the easy one is which we will study. This is the one which we will study. It is not suitable for production code. It is just for what you call example. If you really want a production quality B plus tree, then you should look at github.com/habedi/bptree. The entire B plus tree is implemented as a single header, which you can see here. So the main difference is that it is production level quality code, while the one which I will show is not of production quality. But the advantage of this code is that it is simple. So we will first look at insertion and search. Deletion I will show in the next video. The reason is that if I show everything in one video, it will become complex and it will be difficult to hold that in your mind, because there are no animations or drawings which I'll be showing. I have shown the most of the animation in the previous video. If you have not watched the previous video, you should look at that. So let's look at what H. Abedi has done here. So he has implemented this B plus tree as a single header C library. It supports numeric and string keys as well as custom value types, while the one which we'll see will have only integer keys. It supports insertion, deletion, as well as point and range queries. We won't have range queries in our case. Allows the user to manage memory for values, and it is compatible with C11 or newer. So you should definitely look at it. Maybe later in future, at some point I may explain this, but it is somewhat involving to explain the code written in this. It is little bit involving. I wouldn't say complicated, but yes, it is involving to look at. So to begin with, we will go and look at the insertion and search of what the simple version of B plus tree which we have. So this was the PDF which I had shown earlier, the structure of B plus tree. So this is what I want you to refer to when you try to imagine a B plus tree. This is how it looks like. Okay. So let's get into the actual code. Okay. Now our order is 3 for this B plus tree. So we have a structure node which has a pointer, int pointer, which contains keys. Then we have t, then we have a node pointer children, and then we have n, which is current number of keys. Then we have boolean, which indicates whether node is a leaf node or not. And then this is the next pointer to point in the linked list right at the bottom. And then we have another structure B tree, which has a node root pointer, and it contains the t value, that is basically the order. Okay, and we have named it B tree. So this node is type def2 node, and this B tree is type def2 B tree. Now let's look at the main function, that how we are going to drive this. So the first thing which it does is it creates a B tree, and that then performs insertion. Then we have display, and then we have search. So we will restrict our discussion up to this one. Okay. In the next video, we will see delete key, and yeah, delete is the one which we will see in the next video. So let's look at create B tree, what it does. Okay. So what create B tree does is it allocates one B tree structure here and sets the order to T. Notice that we are passing order here, which was our constant order 3. So T and order are basically same thing. Okay, so it receives the order as T and then sets the order to T. Okay, once it allocates for the B tree node, it creates a node and sends the order, and by default it sends true, which indicates the node is a leaf node. So for allocation of node, we allocate a node, we set the order, we indicate that it is leaf. We allocate the memory for children, keys. So keys is 2 into order minus 1, so 2 into 3 minus 1, that is 5 keys it can hold. Then we allocate for children. The number of children are 2 into t, that is 6 children. Then number of keys is 0 to begin with. Okay. And next is null, and we turn this new node. Now there is a problem here. Straight up, there is a problem. This allocation is not efficient at all. The reason is you don't know whether these children will be required or not. As you can see, this B plus tree can hold 5 keys. So if we put in less than 6 keys, that is up to 5 keys, then these children will be unused. Okay. So the allocation is not very good. It is inefficient. It consumes more memory than required, but it makes the code simple. So beforehand, I will criticize this piece of code that this allocation is not memory friendly. The allocation shouldn't have been here. The children allocation should be at some other place. But anyway, so that's that. Let's look at insertion. Okay. So remember that our root node is created and now we insert B tree 10. So let's go and look at insert. So we have B tree, we have key as 10. So root will now point to B tree root. Now it checks for n, whether n is 5 or not. Okay, 2 into 3 minus 1, 5 or not. So at this moment, our n is 0. Okay, so it calls insert non-full root key. So we look at insert non-full. Okay, now this node is root node and this key is 10. I remember from here. So key was 10. So int I is set to node n minus 1. Now node n is 0 at this moment because initially when we allocated for root node, our n was 0. So where did it go? Okay, so this is minus 1. 0 minus 1 is minus 1. It checks whether node is leaf or not, which is true. Our root node is leaf node. So now it goes in the while condition I greater than equal to 0. Now I is minus 1, so we won't enter this while loop. Then what it will do is it will say that node keys I plus 1 is equal to key. Now I plus 1 is 0 because I is minus 1. So node keys 0 is equal to key. So it puts 10 in there and node n becomes 1 because n was 0, so it becomes 1. And we want definitely enter else part as well. So we bail out and our insertion is complete. Now if you look at the main code, we further insert 20, 30, 40, 50. So till 50, what will happen is that this condition will not be satisfied. It will always go into insert non-full till 50. When 60 will come, it will match. So we consider till 50. So it will always go here. It will look, I will go on increasing. First it was minus 1, then it will become 0. And it will, when it becomes 0, so then it will go inside this loop. Now I is greater than equal to 0, node key is I. So here I would be 0 to begin with. Okay. So at 0, the key is 10. And then this 10 is not greater than the second key, that is 20. We are inserting 20 now. So 10 is not greater than 20. Therefore, it won't go inside. Okay. And therefore, again, it will insert at keys 1, the key 20. So 10, then 20. And then will become 2. So it will go on doing this thing. We will have in the keys 10, 20, 30, 40, 50, and n will become 5 here. Okay. It will start with 0, then 1, 2, 3, 4, 5. So at this moment, our n has become 5. And now we try to insert 60. So what will happen is it will go inside this if condition. It won't go inside else. So what it will do is now it will create a new node, and note that this node is not a leaf node because we are inserting false here. So if you look at the create node code, This is the leaf indication. Okay, this is false now. So our new node is not a leaf node. Okay, now what it does is the children 0, that is of the new root. This is new root. So new root children 0 will be occupied by root. And remember that our root is leaf node. Its n is 5. Okay, so that's what you have to remember, and it contains 10 through 50. Then it will call split child. So the root node, which was our root, is now child of this new root, and it is full, and we want to insert 60 in this. Okay, but we can't insert 60 in this node. We will have to insert it into, we will have to split it. Okay, so let's see how split works. So the root node became the child node, and that's why the name of this function is split child. So here parent is the new root, I is 0, and child is actually root. Okay, remember this, otherwise you will be messed up. So this 0 is 0, and remember children 0 of this new node is root node. Okay, so let's see how it works out, the split child. So t will be child t. Okay, now t is same, that is 3 for everything. Okay, t will never change, order is 3. So it creates a new node, it passes the order 3. If you look at, then it takes 3. Okay, so t is always the same. Now this new child n will be t minus 1, that is 2. We have not yet put in any key, but we are setting n to 2. The number of what you call children is n, or rather number of keys is n, not number of children, number of keys. Now what we do here is we take from j is equal to 0 to j less than t minus 1. So t is 3, 3 minus 1 is 2. So we'll iterate for j is equal to 0 and j is equal to 1. Now it looks at the new keys j. So j will be, since the loop will iterate 2 times, the j will occupy the values of 0 and 1. And what we are doing is we are taking the child keys, that is the original root keys, original root. It was originally root. Now it has become the children 0 of this new child. That is rather parent's child, not new child. So what it will do is it will take the fourth element, that is 0 plus 3, and then 1 plus 3, that is fourth and fifth element it will take and put in the new child. Okay, so it's a copy, we are not moving it. All right, so new child will contain this. Now it will look whether child is leaf or not. So our child, if you remember originally when we created it, we passed true. When we created the root node, we passed true. So it won't go inside this because root is a leaf node. It won't go inside this. Then it will look at child and set its n to t minus 1, that is 2. 3 minus 1, 2. Remember that 2 values we copied to new child keys. Now the n of child, that which was root earlier, is now 2. Now it will look at j and parent of n. Now what parent is our new root, if you remember from here. This is new root. Now new root was created fresh, and when you create a new element, we set n to 0, as we set n to 0 here. So because of this, when we are in this split child code here, if you look at the parent n, it would be 0. Okay, so j is 0. And it says j greater than I plus 1, greater than equal to I plus 1. Now I was 0. 0 was passed to split child. So 0 plus 1 is 1. So it won't enter this loop. Now what it will do is it will say that parent children I plus 1. I is 0. So first child is new child. Now over here we made the 0th children root. Okay. And over here we made the first child new child. So now new root has 2 children, the original root and this new child. The 0th child is the original root child, and first child is this new child. And remember that this new child has 2 keys out of 5 keys we have inserted. We have inserted 10, 20, 30, 40, 50. And from that, we have copied 40 and 50 and put in new child. Okay, 10, 20, 30 are still there in the root node, that is the child node of this new root. Remember that this child node or the original, sorry, what did I do? Oh, okay. Remember that this child node or original root node still contains the node 40 and 50. Those are not removed. We have just copied. Okay. So now we are here. Now what we are doing is we are looking at parent n. Okay. Now parent n would be 0 at this moment. All right. And minus 1. So this j is minus 1. And j greater than equal to I. Our I was 0. So it went into this loop again. Okay. Now what it will do is parent keys I, that is 0, will be equal to child keys t minus 1. So child keys t minus 1 would be 30 because t is 3. So t minus 1 will be 2. And the keys array had 10, 20, 30, 40, 50. So 30 would be put in the parent keys, that is at location 0. And then we increase the n to 1. Okay. After that, we go to insert non-full with new root and key. Okay. Now we come here. Now you see our n had become 1 at the last step. Okay. So I will be 0 here. Now is this node leaf node? That is the question. So we see that when we created the node, the new root node, we said it was false. So it went into this if loop. When we inserted initially in the root node 10 to 50, we entered this if case and we executed these 2 lines. But in this case, we want to enter here. So we'll go in here. Now I at this moment is 0 because node n is 1 and we subtract 1. So this is 0. So I greater than equal to 0, true. Node keys I, that is 0th key is greater than key. We are inserting 60 and what we had is 30 here. Okay. So is 30 greater than 60? No. So we won't into this loop and we increment I after this. Okay. So I was 0, it became 1. Now we check if node children I, that is the second child, I is 1, that means second child because our base index is 0. So if you look at that, which node is that? That is child. Okay. And we look at child n is 2 here. Okay. So is it equal to 5? Because 2 into node t minus 1 is 5. So it is not. All right. So it goes to insert non-full node children I. Now I is 1 over here. Okay. That means we are putting it in the original root node. Original root node. This child is the first child. It contains 50 and 60. It contains 10, 20 and 30. The new child let me arrange my thoughts. The new child contains 50 and 60. This child contains 10, 20, 30. Okay, it also contains 50, 60, but those are copied to new child. So now over here, we are sending children I, that is children 1. That means we are sending this child. Okay. So this child was original root node. And it's at 10, 20, 30, 40, 50. All of those things are with this child. All right. So we look at this again. All right. So now we see that this node is n is 5. Okay. Did we, we entered n is equal to here 2. So this I will be 1 now. Okay. And then we execute the logic accordingly. So at this moment, you understand how to execute this in your mind. You take a piece of pen and paper and draw all these code and see how this code executes. Okay, and we'll see how the insertion works out like this. And then I will explain a bit of what you call search. Okay, my mouse is getting stuck. Give me a moment. Let me reconnect. Okay. So as I went line by line, you need to go line by line and see how it executes the code. And you can make use of a debugger for that. And search is relatively fine. So for search, we take a key. Our search key is 30 at this moment. And we give the root node and we search the key. So what search does is it looks at I is equal to 0. So is I less than node n? It checks the number of keys in the node. And is key greater than the ith key of the node? Okay. If both the conditions are satisfied, it increases I. So suppose our root node is there with 10 to 50 and n being 5. Okay. So I, when it will start with 0, is 0 less than 5? Okay. So yes, that is true. And is key less than node keys I? So the first key is 10 and the key which we want to search is 30 in this case. So 30 is less than 10. So it will increase I. I'll increase I till the third item. So when it will see that 30 is not greater than 30, it will bail out. And it will again check I is less than node n. So at this moment I is 3, which is less than 5. I will see that key is equal to the third key. So it will return true. That is 30 is found. Now let's assume that this while loop and if went in such a way that true was not returned. That is, either this condition was false or this condition was false. Okay. Suppose we wanted to find 35, then it wouldn't work. Okay. Because this condition will become false. Okay. Now I'll check if whether it's a node leaf. If it's a leaf node, then it will return false. Now, since we have only one node right now, that is the root node, assuming we have entered only till 50, then it will return false, meaning 35 was not found. But in our case, it was 30, so it was found. Now, if all these options are exhausted, that it is not a leaf node, if there are other nodes in the B plus tree, then it will go to the first ith child of the node. Okay. And it will try to search there. And then it will become a recursive operation. It will go on recursively trying to find the node across the tree. So with this, I have kind of explained the insertion and the search of B plus tree. In the next video, we will go through rest of this, that is the actual deletion. There are quite a functions which help to delete the key. So see, we are somewhere around line 162 and all this code will go up to line number 415. So we have more than half the code just dedicated for deletion. So I will leave you here and I hope that you enjoyed the video and found it useful. In the next video, I'll complete the deletion. And the one which I mentioned, the HABD one, I would implore you to go through the code, code of this. Okay. First, you go through the simple one and then you go through the code of this one. It might feel complicated if you are reading it for the first time. Okay. But it is not really that complicated. I mean, the reason it's big is there are lots of comments in this. And those comments will help you understand the code. Essentially, it is quite similar. So please go through it and I will make a video on this when I have time. I intend to finish the other data structure first. As a heads up, after B plus tree, we will study segment tree, which is also quite useful in competitive programming. So the next video will be on the relation of B plus tree. Then we will study the theory of segment trees, and after that we will look at the implementation. So once again, I thank you for watching the video. Leave me a comment how you find this video. And once again, thanks a lot for watching. Enjoy. I'll see you in the next video.